On the left side of the circuit, you see what we call an RC series circuit. In a circuit like this, charge gradually builds up over time in the capacitor. It approaches a maximum value that's just equal to the product of the capacitance and the battery voltage, and it approaches that value asymptotically. At a certain point in time, the charge has reached 63% of its maximum value, and that time is called the time constant tau, and it's equal to the product of resistance and capacitance. On the right, you see what we call an RL circuit. It has a resistor and an inductor in series with the switch and the battery. In that case, current through the loop gradually increases with time. It approaches a maximum value governed by Ohm's law. That maximum current is equal to the battery EMF divided by the resistance, and it approaches that value asymptotically. At a certain point in time, the current reaches 63% of its maximum value, and it's a different time constant here. In this case, the time constant is equal to the inductance divided by the resistance. Now, another thing's taking place here. As time goes by, not only is charge increasing on the capacitor, but initially there's zero electric field between the plates of the capacitor. And as the charge gets greater and greater, the electric field in between the plates gets greater and greater. And as the electric field grows, more and more energy grows and shows up in that capacitor. And as you probably remember, the amount of energy in a capacitor can be calculated one of three ways. It's either 1/2 CV squared, or it's Q squared over 2C, or it's 1/2 QV. Well, there's something else we could solve for here. We call it, instead of energy, we'll call it energy density. And let's define that. We'll draw it as a lowercase u. So hopefully you can see the difference between my capital U and my lowercase u. Energy density we'll define as energy per unit volume. So in a capacitor, the volume is easy to calculate. The electric field is mainly contained in the region between the plates. There's some fringe effects out near the edge, but mainly the electric field is here. So you can think of it like this. The energy is actually stored in the electric field. So let's see. It has a area of A and a separation of D. So if we, shade this in, all of that shaded volume contains electric field, and that's where this energy is contained. So let's go with the expression, how about 1/2 CV squared? Okay, so energy density is 1/2 CV squared divided by volume. The volume is just the area of the plates times the separation of the plates. Okay, let's see. This is 1/2 C. Capacitance of a parallel plate capacitor is epsilon naught A over D. And then voltage, voltage is electric field times distance, and that's all squared. And then I need to divide by AD. I think this is going to simplify rather nicely. So the electric field has an energy density associated with it equal to, how about this? We'll call this E squared D squared. And it looks like this A is going to cancel with this A. Okay, what do we have? We've got epsilon naught times E squared. Got epsilon naught E squared. We've got a D squared. Okay, and then we've got another D and another D in the denominator and a 2. Okay, so a 2D squared. So D squared cancels out. Well, there we have it. The energy density associated with the electric field of a capacitor is equal to epsilon naught times electric field strength squared divided by 2. Now we want to figure out if there's any energy stored in a circuit like this. Well, there's not so much an electric field, but there is a magnetic field, right? As the current gradually increases from 0 up to its maximum value. Once it reaches its maximum value, the inductor relents, no longer offers a back EMF, and there's going to be some magnetic field lines passing through the inductor. And just like there's an energy density associated with the electric field, there's an energy density associated with the magnetic field. So let's see if we can figure out, first of all, how we can get an expression for the energy of an inductor. After all, I understand talking about energy for a capacitor because a capacitor is a device that reaches a saturation point and eventually you reach electrostatic equilibrium. However, in circuit number 2, our RL circuit, current, once it reaches this maximum value, then maintains that value, and you never reach an electrostatic equilibrium. So, how about this? Power is equal to current times voltage. So let's try to figure out the power of the inductor. So it's equal to current. Now the voltage of an inductor, in magnitude anyway, is equal to L di dt. Okay. Energy is equal to the integral of power and time. So let's put this together. The energy of an inductor is equal to the integral of I, L, di dt, that's the power part of this equation, multiplied by dt. Well, the dt just cancels out, so we get the energy of an inductor as opposed to the energy of a capacitor. The energy of an inductor is equal to the integral of L I di. Now the inductance can be taken out of the integral sign, and so the energy in an inductor is equal to L times the integral of I di. Well, that's sort of like, what's the integral of x dx? 1/2 x squared. So I think the integral of I di is 1/2 I squared. So that's it. The energy of an inductor is 1/2 Li squared. Hey, wait a minute. This is really interesting. Earlier, in a previous lecture, we said that capacitors only have a voltage when there's some amount of charge stored on their plates, and a resistor only has a voltage if some amount of current flows, and we know inductors only have a voltage if there's a rate of change. But then we made a comparison to some mechanical devices. We can compare capacitors to springs. If a spring is at this length when no weight hangs from it, and then we hang some weight, mg, then there's a force only if the spring has been displaced some value, F equals kx. And if you drop a leaf or a feather or a coffee filter through the air, then there's a downward pull of mg initially, and as it starts to move faster and faster, there's an upward force F that's equal to a drag coefficient times the speed at which it's falling through the air. And then when it comes to inductance, how can we make a comparison to anything mechanical? Oh, so there are some forces that are position dependent, some are velocity dependent, and other forces are dependent on rate of change of velocity, and those are the forces required to overcome the mass or inertia. So it looks like velocity is to current what mass is to inductance. Well, we know there's an equation for kinetic energy equal to 1/2 mv squared. And we just derived an equation that says energy in an inductor is 1/2. What's the analogous quantity for mass? Oh yeah, inductance. And what's the analogous quantity for velocity? Oh yeah, it's current. 1/2 Li squared. 1/2 Li squared looks strikingly similar to 1/2 mv squared. So let's see if we can figure out the energy density of an inductor. Well, once again, energy density is energy per unit volume. So it's 1/2 Li squared divided by volume. And let's try to figure this out for a solenoid. In a previous lesson, we found that the inductance of a solenoid is equal to mu naught n squared A over L. So let's make that substitution. The energy density of the magnetic field is equal to 1/2 times mu naught n squared A over L. So we've got the 1/2, we've got the L. Okay, now we need I squared, and all that divided by volume. Well, let's say this solenoid has a length of L and a cross-sectional area of A, so our volume would be just A times L. Well, it looks like A cancels out, and we have energy density is equal to mu naught n squared divided by 2L squared multiplied by current squared. Let's see, what happens when we use Amperes' law to derive an expression for the magnetic field of a solenoid? Amperes' law says the integral of B dot ds is mu naught times I enclosed. If we choose an Amperian loop in the shape of a rectangle, as you've seen in a previous lesson, this just becomes B times L is equal to mu naught times capital N times I. So it looks like I, if we rearrange this equation, is equal to BL over mu naught N, so that I squared would equal B squared L squared over mu naught squared N squared. Let's make that substitution and see what we get. Let me renumber our work here. Step 1 is an equation for the energy of an inductor. In step 2, we define energy density. In step 3, we made a substitution knowing that the inductance of a solenoid is mu naught n squared A over L. And in step 4, we simplified a little bit. So in step 5, we'll make this indicated substitution and see what we get. The energy density of a magnetic field is mu naught n squared over 2L squared times B squared L squared over mu naught squared N squared. Oh, well, this is going to simplify nicely. N squared cancels with N squared. L squared cancels with L squared. And so finally, this leads us to step 6. The energy density of a magnetic field is, B squared over 2 mu naught. And what was the energy density of a capacitor? The energy density in an electric field of a capacitor, what was that? Let's scroll back up and look. There it is. Epsilon naught times E squared over 2. Epsilon naught times E squared over 2. So something interesting here, in both of these equations, we have an energy density is equal to 1/2. Energy density is equal to 1/2. There's a 2 and there's a 2. And then there's a field strength squared in the numerator. Field strength squared in the numerator. Of course, in this case, for a capacitor, the field is an electric field, and for the inductor, the field is a magnetic field. And then in one case, we have the permeability of free space in the denominator, and in another case, we have the permittivity of free space in the numerator. But otherwise, very similar expressions. We'll see more about energy density in future lessons.